Welcome. Today we're diving into the world of model evaluation metrics and data mining. As data mining continues to shape industries, understanding how to measure the effectiveness of models is crucial. Whether you're building a predictive model or clustering data, the right metrics help you judge performance, compare algorithms, and make informed decisions. In this video, we'll explore the most important metrics, their applications, and how they guide us toward better model. Let's start by understanding why evaluation metrics matter and how they fit into the data mining process. Metrics are the backbone of model assessment. Without them, it's impossible to know if a model is truly effective or just lucky. Evaluation metrics provide objective, quantifiable ways to compare models and track improvements. They help us avoid overfitting, ensure generalizability, and select the best approach for our data. In data mining, where datasets can be complex and varied, choosing the right metric is essential for meaningful results. Let's look at the types of problems we encounter and how metrics fit in. Data mining tasks generally fall into two categories: supervised and unsupervised learning. Supervised learning includes classification and regression, where we have labeled data and want to predict outcomes. Unsupervised learning, like clustering, deals with unlabeled data and aims to find patterns or groupings. Each task requires different evaluation metrics. Understanding the nature of your problem is the first step in selecting the right metric. Next, we'll focus on metrics for classification tasks. Classification is one of the most common data mining tasks. Here, the goal is to assign data points to predefined categories. To evaluate classification models, we use metrics like accuracy, precision, recall, F1 score, and RAW-KUC. Each metric highlights a different aspect of model performance. For example, accuracy measures overall correctness, while precision and recall focus on specific classes. Let's break down these metrics, starting with accuracy. Accuracy is the simplest and most intuitive metric for classification. It's calculated as the ratio of correctly predicted instances to the total number of instances. While accuracy gives a quick sense of performance, it can be misleading in imbalanced datasets where one class dominates. For example, if 95% of your data belongs to one class, a model that always predicts that class will have high accuracy but poor real-world usefulness. That's why we need other metrics too. Precision measures the proportion of true positive predictions among all positive predictions. In other words, it tells us how many of the items labeled as positive are actually positive. Precision is especially important in cases where false positives are costly, such as spam detection or medical diagnosis. High precision means fewer false alarms. However, focusing only on precision can sometimes ignore the importance of catching all positives, which brings us to recall. Recall, also known as sensitivity, measures the proportion of true positives identified out of all actual positives. It answers the question, out of everything that should have been detected, how much did the model actually find? Recall is crucial in scenarios where missing a positive case is risky, such as disease screening. High recall ensures that most positives are caught, but it can sometimes come at the expense of more false positives. Balancing recall and precision is key. F1 score combines precision and recall into a single metric by taking their harmonic mean. It's especially useful when you need a balance between precision and recall, and when the class distribution is uneven. The F1 score penalizes extreme values, so a model with high precision but low recall, or vice versa, will have a lower F1 score. This makes it a reliable metric for many real-world classification problems where both false positives and false negatives matter. RAW-KUC stands for Receiver Operating Characteristic Area Under Curve. It evaluates the ability of a model to distinguish between classes across all thresholds. The RAW curve plots the true positive rate against the false positive rate, and the AUC summarizes this performance as a single value. A higher AUC indicates better discrimination. RAW-KUC is especially valuable when comparing models or dealing with imbalanced datasets. Now let's shift to regression metrics. Regression tasks involve predicting continuous values, like house prices or temperatures. Here, the evaluation metrics are different from classification. Common regression metrics include mean absolute error (MAE), mean squared error (MSE), root mean squared error (RMSE), and R-squared. Each metric provides unique insights into model performance, such as average error size or how well the model explains variance. Let's start with mean absolute error. MAE measures the average magnitude of errors in predictions, without considering their direction. It's calculated as the average absolute difference between predicted and actual values. MAE is easy to interpret and gives a straightforward sense of how far off predictions are on average. However, it treats all errors equally, which may not always be ideal. Next, we'll look at mean squared error, which handles errors differently. MSE calculates the average of the squared differences between predicted and actual values. By squaring the errors, MSE penalizes larger errors more heavily, making it sensitive to outliers. This can be useful when large mistakes are particularly undesirable. However, because errors are squared, the metric is not in the same units as the original data, which can make interpretation less intuitive. To address this, we use RMSE. RMSE is the square root of the mean squared error. This brings the error metric back to the same units as the original data, making it easier to interpret. RMSE still penalizes larger errors more than smaller ones, but its scale matches the data, which helps in understanding the practical impact of prediction errors. RMSE is widely used in regression tasks for its balance of interpretability and sensitivity. R-squared, or the coefficient of determination, measures how well the model explains the variance in the target variable. It ranges from 0 to 1, with higher values indicating better fit. An R-squared of 1 means the model perfectly predicts the target, while 0 means it does no better than the mean. R-squared is useful for comparing models, but it can be misleading if used alone, especially with nonlinear data. Adjusted R-squared modifies the R-squared value to account for the number of predictors in the model. It penalizes the addition of unnecessary variables, helping prevent overfitting. This metric is especially important in multiple regression, where adding more features can artificially inflate R-squared. Adjusted R-squared gives a more honest assessment of model performance when dealing with complex datasets. Clustering is an unsupervised learning task where the goal is to group similar data points. Since there are no labels, evaluating clustering results requires different metrics. Common clustering metrics include silhouette score, Davies-Bouldin index, and adjusted Rand index. These metrics assess how well the clusters are formed and how distinct they are from each other. Let's start with the silhouette score. Silhouette score measures how similar an object is to its own cluster compared to other clusters. It ranges from -1 to 1, with higher values indicating better clustering. A high silhouette score means that data points are well matched to their own cluster and poorly matched to neighboring clusters. This metric is useful for determining the optimal number of clusters and evaluating clustering algorithms. Davies-Bouldin index evaluates clustering by measuring the average similarity between each cluster and its most similar one. Lower values indicate better clustering, as clusters are more distinct and compact. This metric is particularly helpful when comparing different clustering algorithms or tuning parameters. However, it's important to use it alongside other metrics for a complete picture. Adjusted Rand index (ARI) measures the similarity between two clusterings by considering all pairs of samples. It adjusts for chance, so a value of 0 indicates random clustering while 1 means perfect agreement. ARI is useful when you have a ground truth to compare against, such as in benchmarking clustering algorithms. It provides a robust way to assess clustering quality. Confusion matrix is a table used to describe the performance of a classification model. It shows the counts of true positives, true negatives, false positives, and false negatives. This matrix provides a detailed breakdown of model predictions, helping you understand where errors occur. By analyzing the confusion matrix, you can identify which classes are most often confused and adjust your model accordingly. Precision and recall often have an inverse relationship. Improving one can sometimes lower the other. For example, making a model more conservative may increase precision but decrease recall. Understanding this trade-off is essential for tuning your model to fit the specific needs of your application. Tools like the precision recall curve help visualize this relationship and guide decision-making. ROC curve is a graphical representation of a model's diagnostic ability. It plots the true positive rate against the false positive rate at various threshold settings. The area under the ROC curve, AUC, summarizes the model's ability to discriminate between classes. ROC curves are especially useful for comparing different models or evaluating performance across different thresholds. Cross-validation is a technique for assessing how well a model generalizes to unseen data. By splitting the data into multiple folds and evaluating performance on each, we get a more reliable estimate of model accuracy. Common cross-validation metrics include average accuracy, precision, recall, and F1 score across folds. This approach helps prevent overfitting and ensures robust model evaluation. Holdout validation is a simple method where the dataset is split into training and testing sets. The model is trained on one part and evaluated on the other. This approach provides a quick estimate of model performance but can be sensitive to how the data is split. It's often used as a baseline before applying more advanced validation techniques like cross-validation. Bootstrapping is a resampling technique used to estimate the accuracy of a model. By repeatedly sampling with replacement from the dataset, we can create many different training and testing sets. This approach provides insights into the variability of model performance and helps build confidence intervals for evaluation metrics. Bootstrapping is especially useful when data is limited. Overfitting occurs when a model learns the training data too well, capturing noise instead of the underlying pattern. Underfitting happens when a model is too simple to capture the data's complexity. Evaluation metrics help detect both issues by comparing performance on training and validation sets. Monitoring these metrics ensures your model strikes the right balance between bias and variance. Bias-variance trade-off is a fundamental concept in model evaluation. High bias leads to underfitting, while high variance leads to overfitting. The goal is to find a model that minimizes both, achieving good generalization. Evaluation metrics, especially when used with cross-validation, help identify where your model stands on this spectrum and guide adjustments. Selecting the right evaluation metric depends on your specific problem, data characteristics, and business goals. For imbalanced datasets, metrics like precision, recall, and ROC-AUC are often more informative than accuracy. In regression, MAE or RMSE may be preferred depending on whether you want to penalize large errors. Always align your metric choice with the real-world impact of model decisions. No metric is perfect. Each has strengths and weaknesses, and relying on a single metric can be misleading. For example, high accuracy in an imbalanced dataset may hide poor performance on minority classes. Always use multiple metrics to get a comprehensive view of model performance. This approach helps uncover hidden issues and ensures more reliable results. Sometimes, standard metrics don't fully capture what matters for your application. In such cases, custom metrics tailored to your business objectives can be developed. For example, you might weigh certain types of errors more heavily or combine multiple metrics into a composite score. Custom metrics ensure that model evaluation aligns closely with real-world needs. Interpreting evaluation metrics requires context. A good score in one domain may be inadequate in another. Always consider the baseline performance, the difficulty of the task, and the cost of errors. Comparing your model's metrics to industry standards or previous models helps put results in perspective and guides further improvement. Visualizing evaluation metrics can make them easier to understand and communicate. Tools like confusion matrices, ROC curves, and error histograms provide intuitive insights into model performance. Visualization helps identify patterns, outliers, and areas for improvement, making it an essential part of the evaluation process. Many metrics like precision and recall depend on a threshold for classifying predictions. Adjusting this threshold can significantly impact model performance. Finding the optimal threshold involves balancing different metrics to achieve the best results for your application. Tools like ROC and precision recall curves help in this process. Model performance can change over time as data evolves. Monitoring evaluation metrics regularly helps detect drift and maintain model accuracy. Setting up automated metric tracking and alerts ensures that you catch issues early and can retrain or adjust your model as needed. Ultimately, the value of evaluation metrics lies in their business impact. Metrics should reflect the real-world consequences of model decisions, such as financial loss, customer satisfaction, or operational efficiency. Collaborating with stakeholders ensures that the chosen metrics align with organizational goals and drive meaningful outcomes. Clear and transparent reporting of evaluation metrics is vital for trust and accountability. Reports should include not only the metric values but also explanations, visualizations, and context. This helps stakeholders understand model performance and make informed decisions about deployment or further development. Automating the calculation and monitoring of evaluation metrics streamlines the model development process. Automated tools can track performance, generate reports, and trigger alerts when metrics fall below thresholds. This ensures consistent evaluation and frees up time for deeper analysis and model improvement. Evaluation metrics should also consider ethical implications. For example, a model with high accuracy but biased outcomes can cause harm. Metrics like fairness and equal opportunity are increasingly important in sensitive applications. Always assess whether your metrics reflect ethical standards and promote responsible AI. In practice, metric selection is an iterative process. Start with standard metrics, evaluate results, and refine your choices based on feedback and business needs. Collaborate with domain experts to ensure that metrics capture what truly matters. This approach leads to models that are both effective and relevant. Let's consider a case study in classification. Suppose you're building a spam detection model. Here, precision is crucial to avoid flagging legitimate emails as spam, while recall ensures that most spam is caught. By analyzing precision, recall, and F1 score, you can tune your model to balance these needs and deliver reliable results. In a regression case, imagine predicting house prices. Here, MAE and RMSE provide insights into average and large errors, while R-squared shows how well the model explains price variation. By comparing these metrics, you can choose the best model for accurate and reliable price predictions. For clustering, consider customer segmentation. Metrics like silhouette score and Davies-Bouldin index help evaluate how well customers are grouped. By analyzing these metrics, you can refine your clustering approach and create segments that are meaningful for marketing or product development. Model evaluation is not a one-time task. As data changes and business needs evolve, regularly revisiting your metrics ensures ongoing relevance and performance. Continuous improvement, guided by robust evaluation, keeps your models effective and aligned with organizational goals. To wrap up, we've covered a wide range of evaluation metrics for classification, regression, and clustering tasks. Each metric offers unique insights, and the best results come from using them together. Remember to align your metrics with business goals, monitor them over time, and adapt as needed. Effective model evaluation is the foundation of successful data mining. Thank you for joining this exploration of model evaluation metrics in data mining. By understanding and applying the right metrics, you can build models that are accurate, reliable, and impactful. Keep learning, stay curious, and continue refining your approach to model evaluation. The world of data mining is always evolving, and robust metrics are your guide to success.